Morning all. For today's lesson we just want to do a quick revision of Pythagoras' theorem because we'll need it for the next topic that we'll be moving on to tomorrow. So, very briefly, in words, Pythagoras' theorem says that the square on the hypotenuse of a right-angled triangle is equal to the sum of the squares on the other two sides. Okay, that's in words, it describes what the theorem means. And then in our log tables, we have this formula for Pythagoras' theorem, and it's c squared equal to a squared plus b squared. So we'll come back to this in a minute, and we'll come back to the meaning of this. But before we look at Pythagoras' theorem as a whole, we just want to look at a few of the words on it. So first of all, this word here, hypotenuse. So hypotenuse is a name for one of the sides in a right-angled triangle. So that brings us over here to our right-angled triangle. So a right-angled triangle is a triangle that has a 90-degree angle in it or a right angle in it. So you can only use Pythagoras' theorem for right-angled triangles. Okay, it's not going to work for other triangles, only right-angled triangles. And down below here I have two right-angled triangles. Now I haven't labeled them fully to show you where the right angle is in each of these triangles, but I'd be hoping that you'd be able to pick it out if I told you that one of these angles is a right angle. So for the first one here, there are three angles, this one, and this one. Now a right angle is a 90-degree angle. Okay, and an acute angle is an angle less than 90 degrees. And I hope we can see that this is an acute angle here, it's less than 90 degrees. This is an acute angle up here, less than 90 degrees. And this is our right angle, our 90-degree angle in here. Okay, making this a right-angled triangle. Over here I have another example, again, of a right-angled triangle. And again, if we wanted to first of all pick out which is the right angle in it, well, we could eliminate, that's definitely an acute angle, less than 90 degrees. This is an acute angle, less than 90 degrees. So this one up here, if we know that this is a right-angled triangle, this must be the right angle without measuring it. Okay, so those are the right angles. So we've two right-angled triangles here, and now the next important thing is the hypotenuse. We said that is the name of one of the sides of a right-angled triangle, and a particular side. It can't be just any one of the sides in a right-angled triangle. It is always, there's two ways of looking at it. It's either you can look at it as the longest side in a right-angled triangle, or you can think of it as the side which is opposite the right angle. That's the way I prefer to think of it. The side which is opposite, across from the right angle. So if you know where the right angle is, this side is across from it. It's not touching the angle at all. Whereas this side goes right up to the corner of where that angle is. This side goes right up. If you like, these two sides form the right angle. This one then is opposite it. So this is the hypotenuse here. Okay, in our other triangle here, I'll give you a second. Guess which one do you think is the hypotenuse? Again, it's whichever side is opposite the right angle. So in this case, directly opposite the right angle is this side here. This is your hypotenuse. Okay, so it has nothing to do with which side is down on the ground, if you like, or at the bottom, or at the top, or at any. It's whichever side is opposite the right angle, wherever the right angle happens to be. Okay, that's the important thing. So the next thing is then that the square on the hypotenuse of a right angle triangle is equal to the sum of the squares on the other two sides. Now there's a few different ways we can look at that, but for today's lesson, the most important thing we can take from this is that if I knew the length of the hypotenuse here, and I gave the length of the hypotenuse the name c, so if it was c centimeters long, and then the other two sides, if I gave one of them the name A and the other one B, and it doesn't matter which was which, if I call this A and I call that B, and remember, if we are saying that these letters represent lengths, the length of this side, so like this length might be something like 13 centimeters, and this length might be something like 12 centimeters, and this might be 5 centimeters. Well, if I took those lengths, if I took this one, the 13 centimeters, and I squared it, I said 13 multiplied by 13, it would have to be equal to this one squared, 12 by 12, 144, plus this one to be squared. If that was 5, 5 5s are 25. So 144 and 25 is 169. 13 squared is 169. 169 equal to 169. And that's what this means. Now, the important thing, I suppose, with this formula, and we'll go through some real examples where I actually write down numbers in a moment, don't worry. But the important thing is if you're using this formula from the log tables, and it is on page 16 of your log tables here, c squared equal to a squared plus b squared, where c is, as you can see in their drawing, c is the hypotenuse, it's opposite the right angle, and a and b are the other two sides. It actually doesn't matter which one you call a and which you call b. This could be b and that could be a, and the formula would still work. The reason being that you're adding these two together, and addition can be done in any order. So so if we multiply or we square this, it must be equal to the sum of the squares of the other two sides. And if we're using the formula here, regardless, you will see the formula written in different ways in different books, but regardless of what letters they're using for the formula, the hypotenuse is the one that always goes on its own on one side. So if you saw the formula written down as p squared equal to d squared plus f squared, well, it has to be the p squared, or the p would have to be the hypotenuse. It's always the one that goes on its own on one side, whereas the other two go together on the other side of the equal sign. Okay, let's see some examples. So from this, find the value of x. So we've got three different sums to do here. In the very first one, they gave us two sides of a triangle. And again, these are right angle triangles. I should have put that in from the very beginning. Right angle triangles. They're giving you two sides and they're asking you to find the third side. So what we do is we can use our formula. We can look at it up there and we can write it down first, or we can just really launch straight into it, as long as we know that the first thing we put on its own on one side is the hypotenuse. So firstly, which is the hypotenuse here? I hope you've said it's across from the right angle. It must be this 25. So the square on the hypotenuse, 25 to be squared, is equal to the sum of the squares on the other two sides. Order doesn't matter. I could pick this first or that first. So if I go for this, the 24 squared plus the x squared. Okay. And then it's just a simple equation to be worked out. 25 to be squared is 625. 24 to be squared is 576. Plus x squared, I can't do much with it at the moment. If I bring that 576 over to the other side, I have 625 minus 576 leaves me with x squared on this side. So minus is 49. 49 is equal to x squared. So the last thing we need to do is we just need to get the square root of both sides. So the square root of x squared is x. The square root of 49 is 7, because 7 7s are 49. So your answer, x is equal to 7 centimeters. Okay, let's do the second one very quickly. So this time we see that we've got these three sides. The unknown side, the x side, is here. First thing we're going to do is work out which one is the hypotenuse. Again, it's in the same position, I suppose, as the last one. It's directly across from this right angle, so that's the hypotenuse. The hypotenuse always goes on its own. So we put that there, equal to, again, the order doesn't matter here. Last time I took the 24 first and then the x. Now I'm going to go for the 12 and then the 5, just to show that the order doesn't matter. 12 squared plus 5 squared. Now, it's important to notice, look, they're very similar, but the unknown was not the hypotenuse last time, so the x went in here. The unknown is the hypotenuse this time, the x, so it goes on its own. Okay, so next thing is x squared is equal to 12 squared is 144. 5 squared is 25. So x squared is equal to 144 and 25 is 169. And so we just need to get the square root of each. So x, the square root of x squared is x, and the square root of 169 is 13. So in this case, the length of this side is 13 centimeters. So one more then. And again, the first thing we'll do is identify which one is the hypotenuse. This is the right angle here. It's opposite the hypotenuse, or opposite the right angle is the hypotenuse. It's this one. The hypotenuse always goes on its own on one side of the equals. So 5 squared is equal to, the order we do this doesn't matter. We'll say x squared plus 4 squared. So 5 squared is 25. X squared, can't do anything with for the time being. 4 squared is 16. So 25, bring the 16 over, becomes a minus 16. Can't do anything with the x squared for the time being. 25 takes 16 is 9. And lastly, again, we just get the square root of both sides. The square root of x squared is x. Square root of 9 is 3. So 3 centimeters. So the length of this side is 3 centimeters.